Hello everyone, I'm Alina, Ciocarlan, an engineering student at IMT Atlantique, and I'm going to introduce you the work we've done with Thales Theresis Lab on ship detection using self-supervised learning. Ship detection is an important challenge for maritime monitoring, especially when dealing with non-cooperative ships. Few approaches have already been tried, but they either suffer from weak generalization to challenging conditions, or they are only applied to high-resolution images that have a small swath. We decided to focus on detecting ships in Sentinel-2 images using self-supervised learning. This method takes advantages of large and labeled datasets to train a feature extractor in an unsupervised manner. Its pipeline is made of two steps. The first one consists in training an encoder by taking as an input several pairs of images, as you can see on figure 1. Then the network will maximize the similarity between the positive pairs and minimize it otherwise. Encoders trained this way are supposed to learn useful invariances and latent patterns for the final task. Then we have the second task, which is nothing else than a supervised pipeline using the encoder pre-trained in the first task. This pre-trained encoder should help at achieving good performances with few samples. We began our tests on the ship classification dataset published by Agenium Space, and we compared three algorithms. One with an encoder pre-trained on Eurosat dataset using SSL, another one with ImageNet pre-trained weights, and a third one trained from scratch. We varied the number of training samples, and we can see on figure 3 that when having only 12 training patches, SSL network achieves a F1 score 10 times higher than the other networks. But increasing the number of training samples gives the advantage to ImageNet pre-trained weights to surpass our SSL network. We then tried to perform ship segmentation, but since no such dataset exists, we created one. It is made up of 16 Sentinel-2 images of harbors and canals, some dealing with rough conditions, and more than 1,000 ships are annotated. We then cut these images into 2,000 multispectral patches, which will compose the final task training set. We also introduced another pretext task that induces region invariances, as it can be seen in figure 6. We trained the pretext task on 3 well-known remote sensing datasets that have an increasing number of Sentinel-2 samples. On Sen12MS, we performed the simple and the region-based pretext tasks. After that, we used a unit with a ResNet encoder for our ship detector, and we made 2 experiments, training in a leave one out setting and varying the number of training ships. So here are the results for the first experiment. Table 1 shows that Sen12MS pre-trained networks give promising results, although ImageNet encoder allows a better extraction of the features. Both methods also give relatively low false alarm rates, according to Table 2. Here you can see some predictions on Panama, and we notice that weak SSL settings like Eurosat pre-training lead to many false positives on clouds or land, while Sen12MS region-based pre-training leads to competitive results. But ImageNet still seems to be more powerful. For the second experiment, we see that with very few samples, pre-trained networks give a good boost in performances, but Sen12MS with the region-based pretext task achieves 90% of the final conversions with only 200 training samples, while ImageNet needs at least 300 training ships, which means that this SSL strategy is more robust towards frugality. So finally, we saw that self-supervised learning can help in achieving competitive and even better results than ImageNet, especially when dealing with a frugal setting. However, several conditions are required to make a good pretext task, such as having a large pre-training dataset, and knowing how to design performant SSL pipelines can be a game changer for remote sensing applications. Thank you for your listening. If you want to know more, don't hesitate to contact us.